Hello and welcome. We're going to allow a few more minutes for viewers to log in. Please stay on the line. All right, hello, and thank you so much for joining our webinar, The Next Generation of Label-Free Imaging. Before we begin, I'd like to review some aspects of the webinar. We expect the webinar to take about 30 minutes. I'd like to let our viewers know that they are welcome to ask questions at any time during the webinar using our Q&A window. We will answer all questions at the end of the event. If we do not get to the question during the webinar, we will certainly answer the question directly with you offline. If you would like to contact our speakers directly, please use the speaker window and select the email icon. I'd now like to introduce our two speakers, Nick McCollum and Bill DaCosta. Nick has been in the microscopy industry for over 20 years, and Bill has been in the photonic laser industry for over 30 years. Today they will be talking about advancements in chemical imaging applications enabled by the Spero-QT mid-IR QCL microscope.
Thank you, Taylor, for that great introduction. And I thank all of our webinar attendees for attending today. In today's webinar, we're going to share with you a short background on mid-infrared range gathering spatial and chemical information in many applications with the Spero microscope. But first, I'm going to share with you two slides with spatial and chemical information collected on tissues, solids, and liquids. Here are many examples and images that pertain to Spero's capability to provide spatial and chemical information. In the upper left-hand views of this slide are some examples of label-free analysis of tissues, and the lower half shows a couple of examples of material analysis. Over on the right are images of pharmaceutical products being analyzed, and below that are Spero images of particulates and solids as examples of what you will soon see in more detail and learn about today. This video is an excellent example of the speed and detail that the Spero microscope offers. In this 2 mm by 2 mm view of a microfluidic mixing chamber, we are seeing live, real-time mixing of deuterated and pure water. The two liquids are colorized by the software, and you can clearly see at live video speed, in real time, the locations and extent of the mixing. So what is the mid-IR? And what advantage does this range of energy bring to imaging? The mid-IR is from 3 microns to 14 microns, shown just to the right of the center of this slide. The power of the mid-infrared, mid-IR range is that it directly measures the response of each molecule. This power to directly measure the bending and stretching of the bonds of the molecules of interest is referred to as the vibrational resonances of these functional groups. These are the bending, stretching, and rotation of the molecules that is directly measurable in the mid-IR. In this slide, we can see the power of the mid-infrared to be molecular specific, label-free, and quantitative, giving you chemical and spatial information of anything that you wish to image that is responding in the mid-IR range. This slide shows the fingerprint region covered by the Spero, with graphical representations of the biology showing that you can individually select and determine the lipids, collagens, glycogens, and so forth, as well as polymers and other solid-state materials such as polystyrene. What enables this fast and detailed imaging is a key component from Daylight Solutions, the quantum cascade laser, or as an acronym, the QCL. The QCL is a unique solid-state laser invented in the 90s and developed by Daylight Solutions into a rugged, reliable, and tunable, bright mid-IR light source. How tunable and bright are they? Well, here we compare the energy output from these lasers with traditional light sources for the mid-IR. The brightness, combined with our sensitive focal plane arrays and custom optics, is what has enabled DRS Daylight Solutions to create the speed and spatial resolution available only in the Spero microscope that Nick McCullum is about to describe and provide some examples of.
Thanks, Bill, for the introduction and the mid-IR overview. As Bill was saying, a key advantage of the QCL is its relative intensity when compared to other IR sources, such as the standard glow bar of an FTIR or even the multi-million-dollar synchrotron light sources. This high signal noise enables us to utilize non-cooled microbolometer cameras rather than the MCT detectors, which require liquid nitrogen cooling. The Spero microscope leverages several of the DRS Daylight core technologies. First of these are the QCL technology and our expertise in building them. Secondly, our custom wide field high NA refractive objectives are specifically designed for use in the mid-IR. And finally, the DRS military-grade IR sensing technology. The Spero is a thoughtful integration of all these technologies. From the slide, you can see that DRS Daylight produces several different laser-based products, from laser countermeasures that protect military aircraft to environmental sensors measuring pollution. There are unique advantages to using our own lasers in our integrated systems. The lessons learned in the development of one product line feed the innovation of the others, often in a very organic manner. For example, the requirements to ruggedize the lasers for aircraft use have led to more rugged scientific lasers that can survive the FedEx shipping. Likewise, the high-quality optics and detector in the Spero have revealed areas we can improve on our own laser performance, which in turn feeds back to further improvements in the Spero and other products. While we've referred to it several times, you may still be wondering what the Spero is. The Spero is a laser-based mid-IR spectroscopy microscope. While it is laser-based like a confocal, it's not a point scanning system. It's more like a traditional wide-field microscope. However, unlike a traditional microscope, it doesn't require any labels, stains, fluorescent probes, GFPs to be on the sample. Instead, we sweep a broad range of wavelengths across the sample and measure the direct absorbance on the sample at each wavelength. There's a few key features of the Spero. Its speed with our unique single-frequency live view at 30 frames per second and our 35-second full spectral scan. Its resolution with our 0.7 NA objective and our large 40 by 40 detector. It has tremendous signal noise. It operates in both transmission and reflection mode. And it doesn't require any liquid nitrogen cooling like the MC detector systems. So the Spero is an advanced product now, but I want to give you a brief history on how it arrived there. The quantum cascade laser is a relatively new technology. It was only invented in the mid-90s at Bell Labs. Roughly 10 years later, Daylight Solutions was developing the first tunable QCLs, which eventually matured to become the engine for the Spero. After several years of development and product evolution, we introduced the Spero in 2014 as the world's first commercial QCL-based microscope. We continue to develop and improve both our lasers and our optical designs. By 2017, we've released our second generation model of the Spero, which we refer to as the Spero-QT. So the Spero-QT incorporates several improvements over the original model. Its scan time is 10 times faster while doubling the spectral resolution. So in practical terms, the first Spero had a 5-minute scan time, while the QT only takes 35 seconds to perform the same spectral scan. As if this weren't enough, we perform this faster scan at 2 wave number steps instead of the 4 wave number steps of the first generation. The stage also covers 4 times the area and even has higher precision and a faster drive speed. This really enables the Spero to be functionally used as a whole slide imaging system. The sample platform and the stage area have been redesigned to be more open and flexible, leaving room for added complexity, such as manipulators, heaters, pumps, microfluidic devices, and so on. All this, and we've reduced the footprint of the scope so that it fits on a standard lab bench. Now, if you look at the image, you'll notice there's black knobs on the side of the microscope. With a simple turn of the knobs, we're able to flip in a mirror to switch the system from a reflected system to a transmission system and so on. This flexibility allows the Spero to be used for a wide variety of applications, ranging from pharmaceutical tablet imaging in reflection mode to whole slide imaging mode for transmission. Another level of flexibility is our optics. The Spero currently offers 3 different objective lenses. The 12x lens with a 0.65 millimeter field of view, the low mag 4x lens with a 2 millimeter field of view, and a visual objective with an integrated LED light. In this slide, we see the Air Force resolution target showing our spatial resolution on the left. In the middle, we have an H&E, a comparable H&E field of view image, and then on the right, a single frequency IR image for each lens as a comparison. The FTIR has long been the standard instrument for IR imaging and spectroscopy. This slide demonstrates the Spero's image quality and field of view when compared to an FTIR equipped with a focal plane array. Even with a 128 by 128 focal plane array, it would require 16 fields of view and take over an hour to acquire this image to cover the area encompassed by a single field of view of the Spero, which would only be captured in only 35 seconds. Additionally, we can see clear image quality differences. It's primarily due to the high NA optics that we incorporate in the Spero in comparison to the low NA Cassegrain mirror lenses that are found in a FTIR system. So while I'm talking about our images, I want to explain a little bit more about our image format. The image data is collected as a hyperspectral data set, where we acquire a single field of view in X and Y at each wavelength. We do this rapidly and sequentially over 400 wavelengths. This process generates a data cube in which you then have a unique spectral profile created at every single pixel in the image. Each spectral data set contains a full 480 by 480 pixel image comprised of over 230,000 spectra and takes about 30 seconds to create. In comparison, a point scanning system, even with the fastest tunable laser, would require about 13 hours to generate a similar 480 by 480 data cube. So now that we've acquired this data set, let's move on to how we can extract some meaningful data from this label-free image. So on the left, we have an unstained visible image, which provides some topographical information. In the middle, we have a single frequency IR image. This image is taken at 1650 Wave number, which corresponds to the amide-1 protein resonance. So already in this image, we have some spatial and quantitative chemical information. We can see in the brighter yellow regions that we have higher protein concentrations. The image on the right is what we refer to as a digitally stained image. And you can see the label-free image segmentation. This uses the full spectral data cube to create this. And this segmentation is known as a clustering, where we separate single pixel spectra into a specified number of classes based on their profiles and properties. So let's take a closer look at this image and the clusters. So this is the same image, but now you can see a corresponding chart presenting the average spectra of each colored cluster. Most of the clusters follow a pretty similar pattern with slight differences due to specific tissue composition. The small red area in the lower right, however, segments nicely due to its divergent spectra. In this case, the portion of the spectra profile associated with nucleic acids is different. And this area is also, in fact, a region of skin cancer. So it separates itself nicely, and we can use clustering to point it out. So I tend to focus on biological applications. However, the Spero is used to address industrial and polymer applications as well. For example, here we have a visible image of the cross-section of a plastic bag. We can see layers. We could probably measure the total width of it. We could probably identify the width of the layers. This would be useful information, but with a hyperspectral image, we can spatially resolve the chemical composition of this image. Not only can we see that the layer is comprised of different materials, but we can also identify these chemicals by comparing their spectra to existing spectral libraries. So I want to show the friendly interface of our ChemVision software. So I've compiled a brief 2-minute video demonstrating the Spero workflow. So we're start off, we're going to have a live view page of the software open. The laser is going to be turned on, and it's going to be tuned to that 1650 wave number, roughly 6 micron, which is corresponding to a protein resonance. So we're going to get a nice contrast of the protein. So the camera's running, and what we're viewing is a live IR video. It's not a visible image, it's live IR video in the right-hand window. And you can see the image update quickly as we move the stage around. In the left window, we've acquired an overview mosaic image. We'll use this map to select areas of interest to scan, and for the sake of time, we acquired this image in advance. But in practice, it only takes about a few minutes to create. You can see there's a blue marker on the preview image. It moves around as we move the stage. It gives us an idea of exactly the field of view that we're going to acquire. So we can drive around the sample, we'll stop, we'll focus directly on the region that we want to acquire a full spectral scan. So next, we'll move to our sample center page. We'll select sample on the left panel, and on the right panel, we'll set our spectral range, and then we'll hit the start button. So if you look down in the lower left corner of the image, you start to see the laser progress as it's sweeping through the wave numbers. In this case, from around 950 to 1800 wave number range. In the center image, you can also see the image as it changes. The image is updated as it's acquired, and you can actually get live absorbance contrast data. So when you get to a protein area, you can notice high protein or other molecules of interest. You may notice we've intentionally designed the interface in a simplified and contextual manner. So really only offering the options that you need at that point in the process. So now the scan is finishing up. So now we can review the data. As I select points on the image, I immediately get a plot of each individual spectra in the chart. I can also drive through the stack of spectral images with the slider below the image or the black vertical line on the chart. We also have several color palettes and lookup tables that we can apply to the image to enhance our contrast, to demonstrate specific features. Additionally, we can draw regions of interest. In place of just the pixel points, we can do regions of interest. These regions of interest will take an average of all the data within that region and give us a single plot of the average spectra of that data. Finally, we're going to move on to the interesting stuff. These next few slides cover applications being formed by researchers using our Spero microscope. Our first example is an exciting cancer screening study being performed in Germany by Professor Klaus Gerber. They first conceived this project using the FTIR, but soon found the process to be too slow to be used in a clinically relevant manner. They optimized their acquisition using the Spero-QT and determined that it was 160 times faster than the FTIR, but it still provided the same sensitivity and specificity that they were accustomed to. Using unstained fixed tissue, they're able to perform whole tissue imaging along with the diagnostic analysis in under 30 minutes. Having determined the pathologic areas by the previous IR analysis, they then use this map to precisely guide laser capture microdissections on the tissue. The dissected tissues are then run through proteomic analysis to confirm and validate the IR findings. The Spero's non-destructive chemical imaging is an ideal front-end screening tool, allowing for follow-on proteomic tissues on tissue that has not been labeled or disrupted in any manner. In a couple months, we will be hosting a webinar where Professor Gerber will showcase this research in greater detail. Another example of tissue imaging where the FTIR was found to be time prohibitive is the work of Cyril Pétabois at the University of Bordeaux. His method involves imaging hundreds of serial brain sections and reconstructing them into a 3D model where he spatially resolves the tumor. In an earlier trial, this process required a full year of imaging using the FTIR, and the Spero can now image an entire brain through hundreds of sections in a matter of 3 days. In a recent paper, he used the Spero to quantify various metabolites and volumetrically resolve the tumor just through its simple metabolism and metabolites. Continue on this theme of tissue, the Spero's ability to assess protein structure and quality make it an ideal tool for studying skin disorders. Collagen's resonance resides in a specifically identifiable portion of the spectra. This allows us to easily monitor changes in the skin related to aging, UV damage, and skin diseases such as rosacea. So moving on from whole tissues now to analysis of single cells. The resolution of the Spero enables us to separately interrogate cellular properties of individual cells, not just population studies. In this example, we identify cancer cells using shifts in protein and cholesterol profiles. IR analysis of blood serum for cancer and other disease biomarkers has recently become a very hot topic. In this work by Dr. Matt Baker at the University of Strathclyde, he designed a multiplexed array where he was able to successfully identify the cancer versus non-cancer patients by their dried serum spots alone. Beyond that, he was able to identify the organs from which the cancer originated in almost every case. So for these last two examples, I'm switching gears to more of a material science applications. This unique application is where the Spero is used by Professor Hatisha Altug of the EPFL. She's employing the wide field of view of the Spero to assess the spectral properties of an entire array of plasmonic nano-antennae. These antennae will eventually be incorporated into biosensors. So last but not least, we have an example of a recent paper from Dr. Kellers of the GlaxoSmithKline. Using a custom microfluidic chamber, and they're leveraging both our wide field of view to image the reaction area, at the same time our whole high-speed acquisition to obtain real-time, spatially resolved chemical kinetic data, and they really showcase some of the unique abilities of the Spero in this application.
Thank you so much, Nick and Bill, and thank you to our viewers for listening. If you're interested in viewing a live Spero demo, Daylight Solutions will be attending the following events. Next week, we'll be attending Photonics West, where the Spero-QT has been nominated as a finalist for the SBIE Prism Awards. We are honored by this recognition in the photonics industry. We're now going to answer some of the questions that have been posted to our Q&A form. Bill, this viewer asks, so does the laser scan all the pixels at each wavelength?
The laser at each wavelength scans the full field of view and collects that as a single image. Wavelength by wavelength, it does that and stacks those images into a hyperspectral cube, which then can be queried pixel by pixel to pull full spectra of that pixel out.
Thank you so much, Bill. Here's another question for Nick. For features smaller than the diffraction limit, are those features still shown?
So features that are below the diffraction limit are still visible. We're just not able to resolve them from each other. And while we can't resolve them particularly, we can still interrogate them for their chemical spectral data.
Thank you so much, Nick. Bill, this one goes to you. Do you have a spectral library built into your software?
We currently do not. We find most of our users customize their spectral libraries specific to their application. Spectral libraries are commercially available and can be used with the Spero.
Thank you so much, Bill. Nick, this goes to you. Do you have chemometric tools built in?
Currently don't have chemometric tools built into the software. We do have basic viewing tools where we can view the spectra as we showed in the demonstration. But we also work with a third-party software called ImageLab by Pina Software, which has many powerful chemometric analysis tools built in.
Thank you so much, Nick. I also see that there's a few questions that some people were having issues with audio. We'll be happy to send a recording of the webinar to those who are having issues logging in the beginning. Looks like we have another question that just came in. Bill, this goes to you. Can the system be applied for live cell microscopy?
Yes, it can. Typically dependent on the specific cell, as shown earlier in one of the videos, we had microfluidic flow cells. So in those cells, either with flowing fluid or with static fluid, we are able to image live cells.
Thank you so much, Bill. Looks like we just had one more question come in. I'll give this back to you, Bill, as well. Question is, have you measured S and N ratios of the spectra?
Yes, we have. We have 1,000 to 1 is typical SNR, and in some cases slightly better than that.
Wonderful.
Yeah.
All right. Thank you, Bill. I think that concludes the questions for now. For those asking about slides and wanting to get a recording, we'll follow up after the webinar. So thank you for viewing our webinar today. Please take a few moments to fill out a brief survey so we can provide you with the most relevant and interesting content in mid-IR technology. Also, please keep a lookout for our next webinar coming this March, focusing on Professor Gerward's groundbreaking research. Thank you again so much and have a wonderful day.